Just a reminder, you have both the PowerPoint and a couple of other videos along with this, plus you have a lot of worked problems on Blackboard. So where we were yesterday is we were talking about refraction and reflection. And just a kind of reminder about Snell's law and some of the terminology. So if I have an incident ray coming into a surface, and this could be glass, this could be another liquid, this could be a variety of things, the light has an opportunity to do one of two things. It can be reflected, and that's where we get this reflected ray. And if we have our normal to the surface, the angle of incidence is equal to the angle of reflection. Now, with Snell's law, we have to accommodate the index of refraction, and that's how light interacts with the medium that we're dealing with. For air, that number is very, very close to 1. And for a vacuum, it is 1. And for glass, glass is going to be greater than 1. And therefore, what will happen is we will get a angle of refraction, and that's going to come from Snell's law. And if this medium, it has a higher index of refraction than this one, then the light is going to bend towards the normal. If it has less, like say I'm coming out of the glass into the air, it's going to bend away from the normal. And that's pretty much what we had where we were doing with yesterday. We did talk about dispersion and how the different colors are going to be affected by the medium differently. And that's why if I have white light coming into a prism, I'm going to get that spread of the light, and that spread is going to allow me to form my rainbow. So that's where that is coming from. Okay, there we go. So now we're going to talk about mirrors. We always start with a flat mirror. And a flat mirror, we're going to use our angle of incidence and our angle of reflection. So if I have an object out here, in our book, we use O to represent the object. We use I to represent the medium. We use P to be the distance from the object to my surface, and that will be consistent for dealing with a variety of different things. Mirrors, lenses, going from one type of medium to another, but my object to my surface is going to be P. You will see this, you can actually see it in a couple of other ways as well. If you pick up a different textbook, it may be and they may say DO as in distance to the object, or DI as in distance to the image. So just be very careful if you use another textbook or use another resource to understand what their nomenclature is that they're going to be doing it. The image distance is from our surface to where the image appears. Okay, we're going to have two types of images. One image we're going to say is a real image, and one image we're going to say is a virtual image. Now, if I have a flat mirror, we always end up with virtual images, because if I take a piece of paper and I put that piece of paper where the object appears. So if I'm looking in the mirror, the object appears behind the mirror. If I put that piece of paper behind the mirror, light's not going to get to the piece of paper because my light is being totally reflected by the mirror surface. So where that image appears for a flat mirror, it's called a virtual image because the image really isn't there. It just looks that way to our eye. We predict where that's going to look. Now, we can mathematically calculate where that is, and we can do it with geometry. So what happens is I will draw my incident ray coming in. Here's my reflected ray. But if I take my ruler and I extend it back out, as long as my angle of incidence and my angle of reflection is the same, I can actually predict where the image is going to appear. So we use this to denote Q is the distance, and for flat mirrors, the distance between the object and the surface, and the distance between the surface and where the image is, it's going to be the same. For flat mirrors, it will be the same. Now, we also talk about magnification. Now, magnification in these cases is a ratio because we're not always going to make the image look bigger. Sometimes the image is going to look smaller, but when we talk about magnification, it's going to say M is going to be our ratio that we're dealing with. So that helps us out a lot. Now, in your textbook and in these slides, we do a lot of different things related to the sign conventions, because the sign conventions are going to help you with the problems. So if I have my surface, so there's my mirror, if I'm going to be in front or on the real side of the surface, P and Q are going to be positive. If I am on the virtual side or behind the mirror, we're going to use a negative for P and Q. And in the case of mirrors, there's no light getting through the mirror. The light is totally reflected. So when we get to concave and convex mirrors, you're going to see bouncing of those images, but we're still going to use the same sign convention for our P's and Q's. So you will have that. So real images, we already talked about that. One of the best ways to tell if I have a real image is just think about it. And if I can put a piece of paper where the image appears and I can actually see it on the piece of paper, that is going to be a real image. A virtual image is where it looks like it's going to appear, but if I put a piece of paper there, I will never see it. Think about behind the mirror, it's going to be a virtual image. So that's something to just remember as we're dealing with virtual images. We said that my magnification is a ratio. It can be greater than 1 or less than 1. And we're going to define that by being the image height divided by the object height. And magnification doesn't always mean that the image is going to get bigger. If the magnification is below 1, then the image is actually going to appear smaller than the real object. So we have that piece. We're going to use ray diagrams. We already kind of started talking about that yesterday. We're going to use that, and we can actually use constructions on a piece of paper in order to be able to check our work. So it's really cool. So if we're looking at a flat mirror, here's how you would do it. So we usually represent our object by a large arrow. I'm going to put my object in front of the mirror, and I'm going to use 2 rays to help me define my object, or help me define my image. So one ray is going to be from the tip of my object, goes directly parallel to this axis here. This is my normal axis. Parallel to that axis, and we're going to reflect the angle of incidence equals the angle of reflection. And since it's 90 degrees, we're going to come directly back on it. And now I'm going to extend that out to the virtual side so I get that first line. When I come in and do my reflection, I'm going to come in, take a line to where my normal intersects my mirror. I'm going to do my angle of incidence, going to equal my angle of reflection, and I'm going to get my ray actually coming out. And this is the actual light, but this now is my dashed piece, and where these two items come together is where I'm going to actually get my image. So we actually will see the image. So these are called ray diagrams, and we can use those ray diagrams to really help us out. Now, when you actually see the body, the human body in a mirror, you have to be far enough away from the mirror so that you can actually see your toes in the mirror, but you can actually go through the calculation. It's on Blackboard, it's in your book, it's in a number of places, but to see your full body in a mirror, your mirror is going to have to be 1/2 or at least 1/2 of the height of your body in order to see your whole body in the mirror. So for flat mirrors, the object behind or my image behind is going to appear to be the same distance behind the mirror as it is in front of the mirror. Typically, we aren't going to get any kind of magnification with a flat mirror. We have to have radiuses of curvature for mirrors, and that's where our fun houses come into play. If you've ever been to a fun house or at the carnival and you see those curves in the mirrors, you see the distortion. You can see that distortion in a spoon because a spoon is going to have a curve in there as well. Your image will be virtual because if I put a piece of paper behind the mirror, no light truly goes through the mirror, so I'm not going to get a real image. The image will be upright. It'll be in the same direction as my object. And with mirrors, there's an apparent right-left reversal. So if I'm doing my mirror, let's think about, I'm going to show you my hand. This thumb is going to go towards my mirror and back. And so when I look in the mirror, it looks like my hand has been flipped. But if I draw it with my ray optics, you can clearly see where I'm going to get that apparent reversal because all I'm doing is taking the ray, going to the mirror and back, taking the ray, going to the mirror and back, but I'm looking at it from a different perspective. So that's why you get that apparent reversal. So here's our mirror problem where we show that the mirror has to be 1/2 the height of the person. We can do it geometrically. So from my eyes to the base of the mirror, which would be the smallest I could be, or to be able to see my feet, these two angles have to be the same. So this distance and this distance are the same. I can draw the same picture for the top because my top of my head is not at eye level. So I get that part here, but I'm going to get that same distance as well. And as you see on the problem that's solved for you on Blackboard, you can do the geometry and you can actually show that it's 1/2 the height of the person. So you get that. Now, when we talk about spherical mirrors or mirrors with curvature, a spherical mirror is going to, we make the approximation that it's a part of the shape of a sphere. So I can have what we call a concave mirror. So if I'm holding up my hand, this is the concave mirror where my image looks like it's going to be, or my object will be in the cave. This side is the convex side where it's going to be out there. So the concave mirror, think of it as like you're going to generate a cave. Convex is the other side of the curve. And we're going to play with that a little bit to be able to see how it goes. Now, because we're making the approximation that our curve is related to the curve of a sphere, we have a radius. And so we call this the center of curvature. So when we're drawing to do our ray optics, here's my mirror, I have it, and then I have my center of curvature, which is my radius. This is the mirrored side, so we can actually draw that and we can use it from our principal axis. So if I have an object outside of the radius of curvature, we'll have that object come in and bounce. We can do a normal to our curvature and come out, and it is going to produce there. We've got it coming from a different side, and we're going to be able to get an image that forms. Now, sometimes that image may be upright, sometimes that image may be upside down. And we're going to look at that here in just a second. So if I have that curvature now, if we have a mirror that has a spherical aberration, so it's not spherical, or we get a variety of things, what's going to happen is my light's not going to come to a point. And this is what happened with the Hubble telescope. They were able to fix it, but they had to put glasses on the Hubble telescope. But you do see that I get this spherical aberration where I don't get a nice sharp image. So we have to worry about that. And that's one of those things that we deal with for optics. So here's how you deal with ray diagrams for a concave mirror. So here's my object. I'm going to use 2 rays in order to produce my image, or where my image is going to come from. The first ray is going to do just like what we did with my flat mirror. It's going to go down to where I get the principal axis. So here's my angle of incidence. Here's my angle of reflection. These two are equal, so I can draw this line and have it bounce back out. Now, the second ray is going to go through the center of curvature. So here, this will go there. It'll go through the center of curvature, and it will come directly back, and I get that. And so here is my actual image. It's inverted, and you can see that it's actually smaller. This is my P from my object to the mirror. And this is my Q from my object or my image to the mirror. And this is my radius for my radius of curvature. Again, I encourage you to go through and really, really look at those worked problems. Now, when I do my magnification, if I get a negative and I have this negative in here, the negative tells me that the image is inverted. So I'm going to have a flip of my image. And it turns out this is what your eyes do naturally with lenses. And we get that's there. And here is my object distance. Here's my image distance. And I can figure out my calculation. You can derive this formula by looking at the geometry of the previous slide. So if I come over here and I play with the geometry, you can figure out where this magnification comes from, and this actually comes from that geometry. So if we play with it for a while, we actually get something that we call the mirror equation. So 1 over my object distance plus 1 over my image distance is going to equal 2 divided by the radius of a curvature for my mirror. And this is our mirror equation. So if I know the radius of curvature and I know where I put my object, I can calculate where the image is going to appear. And once I have my P and my Q, I can come in and calculate the magnification. And this is where those sign conventions come in. That's where I have to worry about those positives and negatives, because that's going to impact, am I going to get a smaller magnification or a bigger magnification? It impacts whether or not I know if I get an inverted or an upright image. So you do have that. So if I go through this and I do that and I have parallel rays coming from a great distance away, we're going to end up with something that we call the focus, where those rays are going to come in and focus together. And if you've ever played with a mirror, you'll actually see that focus, and we call that the focal length or the focal point. And so that you have that. And so if I take a set of lasers and come in, you can actually see where those lights are going to come in and intersect at the focus of my curve. So it works out really well, and it's fairly easy to calculate. So if I do that, it turns out that the focus is actually R divided by 2. So I can rewrite my mirror equation in terms of my focus instead of my radius of curvature, because I may or may not know what the radius of curvature is, but I can measure where the focus is It's a real easy to measure because if I go out there and I do this, I can just take a ruler from this point to that point and be able to measure that. And then I can plug it in to my mirror equation so that we have that. Now, when I have a convex mirror, we call these diverging mirrors instead of converging mirrors. That concave, where it's focusing at that focal point, is a converging mirror, but I still can do it exactly the same way. The methodology is identical. So in this case, I can use my ray that goes back here, but now I'm going to use my focal point to help me with determining where my image is going to be. I still have where my ray comes in through my radius of curvature, and I can do that, but I will be able to show where my image is going to appear. I still have a P, I still have a Q. This is behind the mirrored surface. So if I put a piece of paper there, that piece of paper will not actually have light on it. So this is going to be a virtual image. And it turns out that it's upright so that you can actually utilize that upright. So convex mirrors, we have already talked about it, are considered diverging because as the light hits that convex side of my mirror, the light's going to bounce off and will diverge. It's not going to diverge. Now, what's really cool is it looks like it converges behind the mirror. So we know where that light is going to appear. So you do have that, and the virtual image is behind the mirror. All right. So when you're working the problems, I encourage you to keep your sign convention tables handy because that's really what's going to help you with your WebAssign and keep your answers correct. So if my object is in front of the mirror, it's going to be positive. If my object is behind the mirror, it will be negative. If my image is in front of the mirror, it's going to be positive. If it's behind the mirror, it will be negative. Same with my focal length. Upright images will be positive and inverted images will be negative. Again, I encourage you to keep this together as you are working your problems because it's really, really going to help you out and get those problems resolved. All right, so we've already kind of started talking about a ray diagram. There is a third ray that we can use, and that third ray we can use as a check on our construction. So basically, we want to get to our image. You do have these in your book, which are very helpful. So for my first one, we're going to do directly across parallel to the principal axis and through my focal point, and voila, that gives me my first one. I'm going to use my radius of curvature as my second one. This works out really well. And then I can use my focal point and bounce out here. And you can see that all three rays come together. I can do the same thing. Now, what's going to be interesting is this shows the object outside of the radius of curvature and the focal length. But now what happens if I put my object inside the focal length? I'm going to end up with a virtual image because of how it works, but I can still do the exact same set of ray diagrams where I put my line, come through, I go through my focus point up to the edge and across. And in this case, I'm going to get a virtual image that's upright, and I can work through that as well. And you do have these diagrams in your book. Same with my converging or my diverging mirror or my convex mirror. You can see where it works just the same. So we use the same convention with our rays in order to have that happen. So as I kind of alluded to, here's a bigger slide of it. If I have my object outside the radius of curvature, My image is going to be real because I can put a piece of paper there and actually see my arrow. It will be inverted and the image is going to be smaller than the object. Now, what happens if I'm inside? I'm going to end up having the image be virtual because if I put a piece of paper here, I'm not going to have the light. It's going to be upright and it's going to increase the size of my image. So it's going to actually look bigger. So we do have that. And then if I have my convex or my convex mirror, we do the same thing. And I'm still going to get a virtual image. The image will be upright and it will be smaller. It turns out that if I'm dealing with convex mirrors, they're always going to be virtual images because this is a diverging mirror and I'm not going to have those rays come together to focus in on the image so that you do get that. So just a few notes. Concave mirrors, I can have either a virtual or a real image. Convex mirrors, it's always going to be a virtual image. Now my virtual images will be inverted my virtual images, I'm sorry, will be upright. It will be in the same direction as my objects are. My real images will be inverted. So you do get that that's out there. So that gives you your introduction to mirrors. Gets those out there. You do have some problems on Monday. We're going to deal with thin lenses and actually we'll deal with images formed by refraction, like paperweights. So I encourage you to look at the paperweight problem. It's a lot of fun. And then we'll also look at our lenses and do that. And then we'll have class again on Tuesday. And then your final opens on Tuesday and it's only over optics. So questions? I will be back in Oklahoma starting on Monday.